Today's lesson on heats of solution will help to emphasize from our lab Friday that either when dissolving a salt of some sort goes into water, either heat will be absorbed, endothermic, or released, exothermic. Simply taking some ionic compound and dissolving it into water, creating a solution, either absorbs or releases heat. And that's the focus again of today's Notepack lesson. Heats of solution is found on page 10 of your Notepack. Be sure that your Notepack is open to page 10. You may want your stoichiometry roadmap if you still find that helpful, and you'll need a calculator for our lesson today. When you have those tools ready, please begin the video. We see on page 10 the heats of change, heats of solution that accompany a solute dissolving into a solvent. The solute, typically some ionic salt, and the solvent will always be water. So we're creating various saltwater solutions. That heat that changes due to the fact that we're simply dissolving is known as the molar heat of solution, delta AHsol. That heat change caused by dissolution, that just simply means to fall apart into the ions it's built from. We're going to take a look and just some practice together. Taking an ionic compound, so we'll need our formula writing skills, and breaking apart into the ions it's built from. Here's our first example problem. And again, it's listed on our Notepack page as number 2, but it's our first problem together. I'll read it with you. When 1 mole of sodium hydroxide dissolves in water, sodium ions and hydroxide ions separate and interact with the water. The temperature of the solution increases, releasing, there's a keyword, releasing 445.1 kilojoules of heat. Let's write this thermochemical equation together. Sodium hydroxide, we'll need to look up. Sodium, of course, with its symbol Na, it carries a +1 charge. Hydroxide is the polyatomic ion OH, and it carries a -1 charge. So when I write my NaOH for sodium hydroxide, I've written an ionic compounds formula. Notice that NaOH starts as a solid. Dissolving a solid into water, I'm stressing here, it's a physical process in which a solid ionic compound dissociates, which just means it breaks apart into its aqueous ions. Now, a couple of things to emphasize as you are checking your thermochemical equation with what I have on the screen. To the far left is our reactant. Although in a physical process, it's just the beginning materials. This is not a chemical change, but a physical change. I'm simply dissolving a salt into water. NaOH, solid. Notice on top of my arrow, best I could, I typed in that water was being added to the solid. When I add water, that's just creating a solution. The ions are aqueous, Na plus and OH negative. A solid material, NaOH, being placed into water, stir, and you get an Na positive ion and an OH negative ion. The delta H, the heat of solution, is written as negative since it was releasing heat. This would get warm to our touch. The thermometer would raise, negative 445.1 kilojoules. So when I write a thermochemical equation for a dissolving process, it's as easy as starting with the solid compound and breaking apart into the ions. Those are two products, Na plus and OH negative. When we release heat, we show that with a negative sign to represent the exothermic. Let's take a peek at our next example. I'll read it with you. In our Notepack, it has a number 3 next to it. The heat of solution for the dissolving process of calcium chloride is negative 82.8 kilojoules per mole. Let's write this thermochemical equation. What would calcium chloride's formula look like? Finding that calcium, its symbol of Ca, it carries a +2. Chloride, its symbol is Cl. It carries a -1. Put them together and we get a compound CaCl2. Remember, we are representing physical changes to simply dissolve. So I take a solid on the left and break it apart into its ions on the right. Calcium chloride is commonly called rock salt. We can visualize a white solid compound. When calcium chloride is in a solid phase, it's hooked together. When it's placed into water, the ions separate through the dissolving process. I create a solid on the left and I break it apart into aqueous ions on the right. The water sits on top of the arrow just to show that it's dissolving into water. CaCl2 solid breaks apart into one calcium ion, Ca plus 2, and I see that I have two chloride ions. The subscript on the left tells me how many of those ions come out on the right. That stoichiometric ratio of 1 to 1 to 2. Ions carry charges. Please emphasize to yourself, I must have charges on the ions on the right side or I'll get them marked wrong. Writing Ca and Ca plus 2 are very different. Calcium ion and chloride ion aqueous, and the exothermic value negative 82.8 kJs per mole. This is a completed thermochemical equation representing a physical process of simply dissolving rock salt into water. Out comes a calcium ion and 2 units of a chloride ion. Let's read our last example on this page. The heat of solution for the dissolving process of ammonium nitrate is positive 25.7 kilojoules per mole. Write the thermochemical equation. Well, I notice positive is indicating it's endothermic. This would get cold to our touch. We begin by finding the polyatomic ion called ammonium, NH4 with its +1 charge. The polyatomic ion nitrate, NO3 with a -1 charge. What does the formula for the compound called ammonium nitrate look like? Well, with a +1 charge hooking to a -1 charge, those two polyatomic ions hook in a 1-to-1 ratio. I have an ammonium ion and a nitrate ion hooked together to create a solid salt, NH4NO3. Ammonium nitrate, when placed into water, water should be above the arrow just by convention so you know we're dissolving. The solid salt turns into aqueous ions. Notice NH4, the polyatomic ion, carries a +1 charge. Very important you place charges on your ions on the right-hand side. NO3 carries a -1 charge. It's called nitrate. The name ammonium nitrate tells you what ions to break apart into. 1 unit of ammonium ion with a +1 and 1 unit of nitrate ion with a -1. Solids turn into aqueous ions, absorbing 25.7 kJs per mole. So you can see, writing out our thermochemical heats of solution, very simple process. Take your solids, dissociate them into aqueous ions. Well, let's put in a little stoichiometry with this. The stoichiometry samples are found on the top of page 11. We're going to be taking those very same thermochemical equations that we had written and put in a little stoichiometry twist. So let's read on the top of page 11 together our first of the 3 sample problems that illustrate how to use stoichiometry with thermochemical heats of solution equations. Number 1 reads, how much heat in kilojoules is released when 2.5 moles of NaOH is dissolved in water? Well, we have just written the thermochemical equation for the breaking apart of sodium hydroxide on our previous page. Glance back at page 10. The first equation we wrote together just a moment ago showed you sodium hydroxide breaking apart into sodium and hydroxide ions. Let's rewrite that equation. Step number one in writing any problem out is to write out your balanced equation, the recipe. Here we see NaOH solid, when placed into water, breaks apart into its aqueous ions, Na plus and OH negative ions. I need you to write that down, the balanced equation, just as we had wrote it a moment ago. NaOH solid dissociates, which means breaks apart, forming an aqueous sodium ion. Do you have your +1 charge written? Your OH negative. Do you have your -1 charge written with the little symbols aqueous? Solids turn into aqueous ions. And along the way, 445.1 kilojoules of heat was released, the negative sign. So there's our recipe. What we know is that 1 mole of NaOH releases 445.1 kilojoules. We're given the moles of NaOH in our problem. The number there was 2.5 as the value given. Given a mole, we want kilojoules of heat. And remember, in our stoichiometry roadmap, not only do moles fit into that heart of the problem, but we've invited in kilojoules as part of the recipe as well. Coefficients and kilojoules all belong in the heart of our stoichiometry roadmap. If we're given a mole and we want kJs, it's a one-step problem. In the heart of our stoichiometry, it's a simple want over given ratio. We want to know kJs set over the given moles. Always, always write down the number given, 2.5. The unit is a mole, and the label, solid NaOH. Given 2.5 moles of solid sodium hydroxide, we set up a want over given ratio. The want over given ratio of negative 445.1 kilojoules divided by 1 mole of NaOH. The 1 comes from the fact that there's a 1 as the coefficient in front of sodium hydroxide. If it had been any other coefficient, that must be placed in the heart of our problem. Hit this on your calculator. Grab your calculator, hit this. 2.5 times negative 445.1 equals. Record your answer. That value will be negative and the unit will be in a kilojoule. When ready, let's read through problem 2. Pause if you're not quite ready, if you're still hitting your calculator from problem 1. Make sure you record your answer and start up again when you have it. Problem 2. How much heat, in kilojoules, is released when 100 grams of sodium hydroxide are dissolved in water? Again, we'll need to write our thermochemical equation for this process. The first step always when solving a problem is to have a recipe in front of us, the balanced thermochemical equation. And this will be the 3rd time that you've written this very equation. When solid sodium hydroxide is dissolved into water, we see that aqueous sodium ions and aqueous hydroxide ions are released. Solids break apart into aqueous ions. You may put the water above the arrow indicating that it's a physical process where a solid is simply breaking apart. The word is dissociating into its aqueous ions. And along the way, 445.1 kilojoules of heat was released. So there's the recipe. Given 100 grams of NaOH, we want to know kilojoules of heat. Given a mass, calculate a kJ. The stoichiometry roadmap, I missed typing in a 1, is step 1, convert to a mole. Step 2, the heart of our problem, want over given ratio. A step 1, step 2 on the stoichiometry roadmap. Since we're given a mass, we've got to get into the heart of the problem. Let's begin by writing, as we always do, the amount given. We'll start by writing 100, the unit grams, and the label solid sodium hydroxide. In the first step of our stoichiometry roadmap journey, step 1 is to divide. Now where did I get the 40 you see on the screen? How do I change a gram into a mole? Well, I've done that for you. I've simply added the formula weight, called the molar mass of an Na plus an O plus an H. 23 plus 16 plus 1, the atomic weights of those three elements, and that's where the 40 came from. 100 grams is the given. In step 1, I'm simply converting into a mole so I can get into the heart of my problem, my want over given ratio. I want to know the kJs. It gets placed on the top. Given the moles of sodium hydroxide, notice the coefficient in front of NaOH is a 1. If it is any other coefficient, grab it and place it into the heart of your problem, just as we did in any other stoichiometry relationship of want over given. Now grab your calculator. I've not put the answers on the screen. You have to hit them. The key sequence. You begin by typing in 100, divide by 40, multiply by negative 445.1, and your answer will come out in kilojoules, and it should be negative to remind us it is indeed exothermic heat releasing. Given 100 grams, we step 1, step 2 on our stoichiometry roadmap to land at a kilojoule. Pause here if you're still hitting and start up again when ready to look at problem 3. Problem 3 asks, how many grams of ammonium nitrate must be dissolved in water so that 88 kilojoules of heat is absorbed? Well, as usual, we need our thermochemical equation. Ammonium nitrate dissolving in water was written just a moment ago on our previous page. I believe it to be the very bottom thing we wrote on page 10 of the notes. So let's rewrite. We know that NH4NO3 solid, that's called ammonium nitrate, when placed into water, and again, water could be above the arrow to remind you of just simply dissolving. It's not a chemical change, but just a physical process of creating a solution. Solute goes into solvent. The salt drops into the water and we get out ions. NH4 plus is an aqueous ion. Do you remember to write its charge? Nitrate is NO3 with a -1 charge, an aqueous ion. See, ions only exist in water solutions. I must indicate that they're aqueous. And out of delta H, we see 25.7 kilojoules for every mole of ammonium nitrate that dissolves is absorbed. It's getting cold to our touch for endothermic. The quantity given was 88 kJs of heat. What we're being asked to solve for is grams of ammonium nitrate. Given a kJ, solve for a gram, a kJ mass problem. If I think about the stoichiometry roadmap, I'm in the heart of my problem to begin with. I'm given a kilojoule. That places me right in the heart. And I want to go out to a gram. So the stoichiometry steps would be step 2, step 3. Remember, in step 2, it's our want over given ratio, and then we'll multiply to head out to find the mass of ammonium nitrate. Here's what we're given. 88 kilojoules is our given quantity. Our first ratio, a want over given stoichiometric ratio. I want to know ammonium nitrate. Its coefficient is a 1. From the balanced equation, place the coefficient of what we want over the kilojoules of heat, positive 25.7. See how the kJs cancel in the heart of our problem? And we've converted to moles of ammonium nitrate. Step 1 is the want over given ratio. Now, where did that 80 come from that you see on the screen? In the heart of our problem, we converted kJs into moles. To go from moles to grams, you got it. That's the molar mass. Sometimes I say formula weight of ammonium nitrate. I added that for you. Couple of N's at 14 apiece, 4 hydrogens at 1 apiece, and 16 times 3 for the oxygens. When I added NH4 and O3's formula weights, I found 80 grams per mole. Every step has a number, unit, label where appropriate. You got it. Grab your calculator. I don't have the answers recorded. You have to hit them to record your key sequence of 88, divide by 25.7, and multiply by 80, and record your answer as grams of ammonium nitrate. What to do next when we get this? I want you to take out your practice test B and find objective 5. Friends, be sure you're looking at practice test B at the first time. I want you to use the Moodle and actually open up practice test B's video instruction. You're going to scroll down and you'll see the video lesson on objective 5, forming heats of solution. The very same practice as the last 3 examples worked together from the note pack. I want you to do the video lessons first using practice test B. I don't have video lessons on A for this particular objective. I only put them up for practice B. So do practice B first with me, completing objective 5, and then on your own work the practice test A, objective 5, and we'll check that again tomorrow. Do B with me and then do practice A on your own. So at this point, pause this video lesson and pull up practice test B, objective 5, and work those with me.